All right, we are back for day 6. One thing that I do want to mention before we get started, we had day 5 yesterday. And after I make these videos are very much like the train of thought as I'm going through and solving them. So we end up with something that works and passes, but not necessarily something that is optimal, not necessarily something that is the most understandable or readable code sometimes. Especially this was true for yesterday when I was going through and trying to make sure that we had all of the rules so that we could react to any of them if they were going to be like odd in some way, because that has happened in past advent of codes. But it turns out that yesterday can actually, as we observed, be solved through just really sorting, which we kind of proved out in our solution in part 2 by doing literally the sort. So I went back for part 1 and part 2, and maybe you can see the change here. This is all of the code for the filter map that we had in part 1 for the first video. This is the code for all of part 1. Now that we've relied on that assumption that this sorting is the only thing that needs to happen. So the code gets cleaned up a lot. I do additional benchmarks. You'll find those in these extra files. So if you look at the repo, it'll be part 1 and then part 1 of variant. I've already been doing this for other days. For example, day 1 has a number of different nom parsers in it for different days or different variations. So I just wanted to point that out. That is happening behind the scenes. I don't always make a video on the refactors, but sometimes I do if they're interesting enough. So let's take a look at day 6. The historians use their fancy device again. This time they whisk you all the way to the North Pole Prototype Suit Manufacturing Lab in the year 1518. These are links to previous puzzles. So this is 2024 day 4, and this is day 5, 2018. A single guard is patrolling the lab. Maybe you can work out where the guard will go ahead of time so that the historians can search safely. This is a map. This is starting to sound familiar. The map shows the guard, which is this caret. Guard is currently facing up. Obstructions are all shown as octothorpes or hashtags or whatever you want to call them. There's a very strict protocol for how the guard moves. So if there's something directly in front of us, turn 90 degrees to the right. Otherwise, take a step forward. So moves up, hits an obstacle, turns right. But is it just a turn or is it a turn and a move forward? I guess it doesn't really matter unless we're counting steps. Yada, yada. By predicting the route, you can determine which specific positions will be in the patrol path. The positions are marked with an X. And then eventually it seems like the guard leaves the area through one of the walls or whatever. In this example, the guard visits 41 distinct positions. Predict the path of the guard. How many distinct positions will the guard visit before leaving the mapped area? So our test input is this one. Just create day 6, source part 1, drop this in. I think we're just going to start out with simulating. Seems very straightforward. We don't need to do any more than that for part 1. We have our rule set, which is either move forward or turn right. So I guess we have a facing direction like north, south, east, west, and then a current position. I know that we can probably speed this up by doing like searches and filters and things like that. But I don't know if the rule set is going to change for how the guard moves in part 2. So I think I'm just going to start out with step-by-step simulating the guard, which also actually will help me in the future if I decide to do like a bevy visualization of this or some kind of visualization, because I'll have each step anyway. So while we might want to shortcut it for performance reasons, I actually don't want to shortcut it if I want to show the guard moving frame by frame or something. We do need the dimensions of the grid, I think. But I think since we're not going to skip anything, we can probably not even parse this for the most part. So I imagine the fastest way to do this is actually just to do a single scan through this whole thing. We will find out where all of these positions are. We probably don't even need to do that though, because we really only need to know where the caret is. We could use the dimensions of the grid, but I also don't know that this is entirely encapsulated either. Is this an infinite grid? I guess if the character leaves the outer, like if it's past any of the others, it's done, right? So we're going to test for that anyway. So question in my head, do we want to keep the extremes? Do we want to keep, I guess, effectively the grid dimensions? Let's start writing a little bit of code here. Now, one thing that's really cool about nom is that we can actually use alternative input types, and one of those is provided by nom locate. So if we want to do it this way, we can actually get the position of the things that we're parsing rather than having to manually track the indices ourselves. And that's done through just replacing the input type. So we're using a string slice, we would use this span instead. And this span is just a type alias for a located span with the input. So for me, I would need to include nomlocate from our workspace. I already have it in the root of my cargo toml, so it will be here for me. You might have to install it if you're going to follow this. And normally our parser would look something like this. I think I used the wrong dash here. Yeah, it's an underscore, not a dash. So we can pull the usual I result in and located span here. Located span comes from nomlocate. All right, so I had to clean up a little bit of space on my laptop. Have to get more terabytes next time. But like I was saying, this span is a type alias to a type that comes from nomlocate. That'll give us the positions of everything in this grid. I think this is not necessarily required for today, but it is very useful in general and might be more useful later, even later on today if there are multiple things to parse out of this. And I want to introduce it while it's still a problem that doesn't require it. And Nom has this really interesting parser here called one of, which we can make use of. So we've got a separated list separated by line endings, and we're looking for one of these characters. And that gets us one of the dots because that doesn't quite reach the line ending. So if we wanted to, we could do a many one here, and that would give us everything. And now we're parsing every single line. So if we take our input type and we change it out from span, or from string slice to span, then we also need to wrap our input up here when we pass it into parse. So to make it a little bit clearer what's happening here, I split the token parser out that we are using, one of each of these characters, into its own parser. We then get access to nomlocate's position. I mean, we can call it a parser, but really it's just getting the positions of these. In this case, it gives us the line. And we can kind of see what happens if we move this position around. So this position is operating on the input. The offset here is 1. The line is 1. The line starts at the number 1, but the located span also comes with additional information. So we can call location line and get column. And now we can see that we've got the line, the column, and the token. Similarly, if we move this, we can see the column increase. So depending on where you call this on this input type, the input for nom is continually getting shorter as we parse into it. So it would make sense that if we try to get the location after we've parsed, we get a different number than if we try to get the location before we parsed. So now we've effectively got the X and the Y positions. And because we're working with those positions, I'm going to use glam. Again, this is not strictly necessary, especially if you want to do a more optimized solution. And in this case, the line and the column are U32 and U size, but we're never going to have anything that isn't effectively an I32 anyway. So we can include that information and we can return it just like this. So now we have, let's say, I also forgot to subtract 1 from both of these because they start at 1. So if we look at our input, there's this hash on, let's say, the second line. We can filter out all of these dots because they don't matter to us at all. So we'll have position value here and value not equal dot would filter all of that out for us. Of course, this needs to be a reference or the other one needs to be dereferenced. And we can use turbofish syntax to put this into a vec. So we have a vec of ivec2s and cars. And now instead of logging out those items, we can log out walls here. And actually what we end up with is all of the positions of all the walls, which is great for us. So let's see, 4, 0 would be 0, 1, 2, 3, 4. That's correct. And then 9, 1 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the first one, also correct. The player is also in here at 4, 6. So 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4. So we've got the positions of everything that we actually want to care about. And we can adjust this parser later on to actually kind of not allocate everything for all the stuff that we're kind of skipping. I think I'll also, because I'm not too concerned about this being incredibly efficient at the moment, because we haven't even solved the problem yet, we can do a find here. And instead here, I'm going to do .expect because this always has to be true. Again, this is advent of code, so the input should always be well formatted. Expected of vec found tuple. Expected of vec of ivex and cars found a tuple. All right, because I didn't flatten. I need to flatten this first because we do have a vec of vecs coming back from that parser. And then this is actually shared reference. So we had the flatten down here. I just forgot to use it up here. And then here, instead of filtering out for everything that isn't, we'll filter out for the things that are. So we have the player here in the walls. So let's do player, walls. And we've got player at 4, 6 and a bunch of walls with their ivex. And we kind of have an issue here because I used .iter here. So the issue is value of type hash map ivec2 car cannot be built from an iterator of a shared reference to this tuple. And that is generally speaking an issue with ownership. And once we do that, we find out also that we're using items in player. And if we look at player, this is a shared reference to that tuple. All of that data is being constructed basically in this parser. So we can fix that with .cloned. And then we end up with ivex and the walls that are there. So this is only a hash map of ivex. So if we find something, then there is a wall there. So we'll pass back the input, the player, and the walls. And that is the player, which is a position, and the character. In this case, the character doesn't really matter. We're just kind of keeping it around anyway. This is not the most well-written parser. I just wanted to get across that we can get locations out of these parsers with nomlocate. That is the only purpose of writing it like this today. Then we've got a hash map of ivex2 and cars. So we should have player, walls. You can probably subdivide player into player position and a thing we don't care about. Probably make this mutable as well. Probably just futz with this directly. We can take advantage of the ivex and the associated constants on those ivex to start our direction off. So in this case, our direction is going to be facing -y. So we're going upwards. We have our player position from our parser and we have the walls from our parser. So we could do a loop here. The condition we would have to check is that the player is not outside of any of the wall boundaries. So I think we can just calculate that here. So Glam does some nice things like operate or let us operate to get the max value of the x's and the y's component-wise, min values, stuff like that. Rust standard iterators give us also the ability to do min and max over that iterator. And itertools gives us the ability to return the minimum and maximum. Now, unfortunately, there is no greater than, less than implementation for ivex, so we can't just call min max directly. But we can do x min max, y min max. So walls.iter.map to use the x and y, and we get 0 to 9 for both of them, which we could have gotten this number other ways. But I think we can do now while, let's see, x min max, and we can use the into option for each of these. Because min max, if we go look at it, is actually an enum, which could have no elements, 1 element, or 2 elements. In our case, we want this to be unwrapped because we know there will always be the values we're expecting here. So if we do x min max 0, x min max 1 contains player position, and same thing for y position. Both of these need to be references. And then I ran myself into the situation where we have an infinite loop again because I forgot to write a break in here. I have done that too many times in the last 2 days. So I'll just kill 9 that and it will stop. And now that I have a break, I feel a little bit more comfortable running this again. So we'll get rid of this min max. Now I think that we actually want to include that final position. So I'm going to do ... equals for these ranges. And then here's our loop to move our character around. Now there's 2 things we need to do here. One of them is create a hash set, I think, for visited positions, which is just going to be ivex2. Hash set does need to come in. I guess we can also do from the current player position, stick that in an array. So now we should have a visited positions that has the current player position to start out with because the player is standing on that position. And a set means that every time we insert into this, we don't have duplicates, so we will only have the number of positions that are actually visited. So if the player is in the grid, then player position, then we need to check for the next position, which will be player position plus equals direction. We're going to get the wall using that next position. If there is a wall, we need to turn right. Otherwise, the next position is valid. So player position equals next position, and visited positions inserts the new position. And then this continues until that clause changes. Looks like we have expected ivex2 found unit plus equals is not what I was going for here. So thank you, Rust compiler. Visited positions needs to be mute because we are going to change it. We are also going to need to turn right. So we probably need to match on the direction. We could do an enum here. And I think actually, now that I think about it, that's probably what I want to do. Right, so we get direction, north, south, east, west. We'll derive debug on this because why not, in case we need to debug it. We can also impl direction here, which will be interesting for us. I'm going to comment that out up there for the moment. And impl direction will be turn right, which will take self and return a direction. So if we match on self and fill arms, we see all of these. And then we can, actually, it occurs to me that there might be a rotate in here. returns the right-hand side rotated by the angle of self. Probably could have made use of this, but I'm going to continue with this for the moment. We're going to go clockwise. So north goes to east, south goes to west, east goes to south, west goes to north. And then we can also have 2 IVEC2, which will return an IVEC2. We'll match on self again. And we have 0, -1, which we can also use the constants here. So this will be neg y, this will be y, this will be x, and this will be neg x. So now we have these two functions that we can use on directions. So direction.turn, oh, right, direction needs to be our direction before that shows up. So direction, north in this case, and direction.turnright.to IVEC. I guess we don't need 2 IVEC here because we've changed that value. This needs to be 2 IVEC to get that player position. There's a warning on this direction, so let's figure out what that is. Value assigned to direction is never read. The test is failing. So if we look at visited positions, it looks like we're bailing out because I break here. Right, so we break immediately. So Rust is actually correct in this warning, which is really cool. This direction is set. Then we do this while loop, or we start this while loop. We get to the point at which we hit this direction, and we set the direction, and then we break immediately, which means that that direction actually is never read. That is correct. So if we check visited positions.length, this loop is now pushing us in the directions that we need to go. And it looks like the answer is 42, which is the answer, if I remember correctly. Did we not update the test with the correct? Okay, I think this is supposed to be 42. 41 distinct positions on the map. So I wonder which position that is. That is incorrect. I wonder if our bounds do actually need to be -1. It'll be the last one, so we should be able to just look at it, I think, because it should be a new position. Oh, we do actually need to fail this test, though. This is supposed to be 41 anyway, so we are actually failing the test anyway. So it looks like 8-1. No. To figure out which one is the last one, we aren't keeping an order here. We aren't using this input either. Let me comment that out or underscore that. Visited positions doesn't necessarily keep an order for that. So I think that debugging the player position will do that for us. And then we don't need to debug that whole hash set. And our last position is 710, which is the position that kicks us out of the grid and stops the loop. So I think we just want to do -1 here. I think we want to see this to make sure that we are out of the loop, because 7-9 would be in, and then if it went to 8-9, it would also be in. So we don't want to like restrict it that way. We don't want 9 to be the issue. We just want to make sure that we don't count that extra. So that will pass. We've got some Clippy warnings for complicated types. Oh, right, position. We'll cover the Clippy stuff in a second because that's really important, actually. Important is, you know, here or there, but there are some changes we can make there for sure that are really easy. So we can do day 6, part 1, and that gives us this answer, which is correct. So we got a gold star. Yeah. So it looks like there's potentially new parsing. Okay. So what have we done? We've constructed a very crude parser today. The thing that I wanted to get across in this parser is that we can use nomlocate span to get the location information for any parsed entity. This could be really useful for us in the future. And it seemed like a good introduction to the idea that it exists. This isn't necessarily the best way to do it. We do actually also do extra computation after we've done this parser to, you know, find the player and whatnot. I'm not terribly upset about this. I think it's fine. I'm sure we could run this cargo bench and it would be probably reasonably slow in general. Of course, if we do that, I should probably remove the debugs that are constantly getting churned out. Printing the console is not particularly fast. So yeah, this is not a particularly fast solution, about 700 microseconds. Well, for advent of code, it's not particularly fast. And if we want to, I can grab this and grab our parse function here, and I'll do parser part 1, I suppose. And then in our part 1, I'm going to make that public. So this is our parse function. In this case, we will have to actually bring that span type in for this black box. Oh, not tracing span. We do need to then make sure that our type alias, which is something that we created here, is public, so it can be accessible. And we can see that the parser is actually a large chunk today, about 400 microseconds. We're doing this not particularly quickly, not particularly efficiently. but I think that's fine for today. I can always refactor it and get it down after it's fully working, which is definitely the way that I prefer to do Advent of Code stuff, get it to work and then optimize. So once we get the player position and the walls, we can do a check for all the walls and get the min and max positions for them. In the test case, that is 0 to 9. We could get that different ways. We could get that from doing a count of the lines. We could get that from doing lines.next and then doing a count of the first line, etc. There's a couple of different ways to get this number. Then we created our own enum called direction for the direction that our character is facing in. We aren't counting the number of steps, just the positions that our character has been in. And then we have a hash set here of ivec2s that we start off with the player position. And we basically do a loop until the character runs out of the grid. And we use those min and max ranges to check whether it's in the grid or not in the current position. This does cause us to actually include one extra position in our hash set. That's the position that leaves before this loop breaks. So we could choose to do a loop keyword here instead and break inside of the loop, but both options I think are valid. And then we do a subtraction on the visited portions, and that's it. The interesting part here for the direction is we created a direction enum with 4 variants, and we implemented a couple of functions on direction to make it easier for us to work with. One is turn right, which makes the code here very readable when we want to actually do that. So direction.turnRight returns us a new direction, which we can just set as the next one. And then we also implemented 2ivec2, which turns this direction into an ivec2. So we can always work with a direction and get the kind of value that we need out of it, depending on what we're doing. Makes the code a little bit more readable. And then we use the ivec2 constants for the directions that these are actually going to go in for the ivec. So with that, let's take a look at part 2. They want to place an obstruction in such a way that the guard will get stuck in a loop. To have the lowest chance of creating a time paradox, the historians would like to know all of the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. The guard is there right now and would notice. Guess we should have called that guard, not player. In the above example, there are only 6 different positions where a new obstruction will cause the guard to get stuck in a loop. The diagrams of these 6 situations use 0 to mark the new obstruction, pipe to show a position where the guard moves up and down, dash to show a position where the guard moves left to right, and plus to show a position where the guard moves both up, down, and left, right. So the guard is going in this circle here. So basically, we need to place an obstruction in every location. Technically speaking, we only need to place the obstruction in places the guard has already been. I think there is no other valid option. So we can cull the number that we're going to have to process here. The important thing is having enough options that you can find one that minimizes time paradoxes. Okay, I forget what that means. So get the guard stuck in a loop by adding a single new obstruction. Obstruction can't go where the guard currently is. Obstruction needs to go in a place where the guard actually goes in the first place. And we need to write the process that we've already done and add a condition to see if they return to a place they've already been. But that place has to be the starting location in the same direction. I don't think that's true, actually. God, these diagrams don't show where the guard goes at all. Okay, so the guard here gets stuck in this 3 by 5 loop. So it's not actually getting back to the original position. It's getting back to a position you've already been when the next position is also a place you've already been. Okay, so let's get started with taking the code that we wrote for part 1 and putting it into part 2. The answer here is the number 6. So really, we are going to basically have to reuse this loop, but write it slightly differently. And I think we actually don't need to detect loops. It obviously is more correct to do the loop detection. But if we set a high enough number, then they can all run. And the ones that stop would be the ones that don't have loops. So we need the original player position, actually. So I'm not going to mutate this. I'm going to take this and I'm going to say, this is the original guard position. We can actually keep this mutable now because we have the original guard position saved. The walls are also saved. I think then we need to probably clone these with the additional. This could probably all get pulled out into a separate function. So we have here visited positions. These are all the positions in which we could place something. So we have to place one in all of those positions except for the guard's starting position. Can we remove one from the set? Okay, original guard position is one that we need to remove. And then there's that one that's out of bounds that we also don't want to have. So we could probably take this logic here and just copy and paste it here for the bounds check. I mean, because we're doing this check now inside, we probably don't need to do the check outside, but right. So all of this can go away and this just turns into a regular loop call because we've taken the detection here. We have our logic running. If there's a wall, turn right. Otherwise, if we are inside the grid still, I think with the next position, right? If the next position is in the grid, then we insert it. Otherwise, we break. I think that's right. Yeah, so now we don't need this -1 because our numbers are correct, right? So part 1 is 4973 and part 2 is 4973. So we've kind of fixed our logic here. I guess we could pull this up to else if this, else break, and we get rid of that. So this should also work. Yeah. So we have our logic here. We calculate the next position. If there's a wall, we turn right. If we're in the grid, we insert the next position. If the next position is in the grid, we insert the next position and move on. Otherwise, we break. And that gives us all the visited positions. We should take this logic and move it to part 1 as well. So now we have the visited positions that we need to do that for. We need to remove the original guard position from that because we don't want to place anything there. And then we need to iterate over each of these and place a wall there, right? This IVEC. In this case, we're just going to clone, like cloning the entire hash map is probably overkill. We could probably just reference it and add the new wall. So let's do that instead. And we'll need to do this loop. And with this new visited positions and this new directions and stuff, right? So mapping over this, we need to do the loop. This isn't being used at all. So I don't know what this is going to be just yet. Still an iterator, and it's an iterator of unit right now. So the question is, does this loop? And I think the answer is if we break out, right? If this if isn't true at some point and we're supposed to break, then this is not a loop. So is there another condition we can check before that to determine if it is a loop? And I think we talked about it before, but if the player position that we're in is in the hash set already and the next position is in the hash set. So probably the easiest way to track this is to have a variable called is in previous location. And if it is, then we break true. But we also need to check if we are in a location that is in our hash set already, and the next position is also in the hash set, then we were on, I don't think that's strictly true though. We could go up one Y and down another Y, and then we would be in that situation both times. So we would actually have to keep track of the locations that we've been in and the directions that we were facing when we were in them. And then I think our logic here might get simpler, because if we're in a location that we've been in a direction that we've already been in, then we're looping. So I think we need to change the visited positions. In this case, this is going to be a hash set of IVEC2 and direction. And this is player position direction, because that's the starting position. And I think that we probably need to implement hash for direction, which is totally fine. I think partially eq and hash all make sense for direction. So our hash set now of visited positions is going to be a hash set of a location and a direction that we're facing in. And if we are ever in a location that we are facing the same direction we've previously been, then we're in a loop. No, that's not technically true either. No, I think it is. So we're going to do player position here and direction. And is in previous location is no longer necessary, because this needs to come first, I think. If next position, this also needs to be walls.get, next position is some, or next position equals the new wall. And our check here needs to be if next position, not walls.get, visited positions.get, next position and direction. When do we need to do this check? We have the next position immediately. We don't know what direction we're going to have to go in that next position. So if our next position is a rock, we turn right, we're in the current position facing right. That could be it, right? So we need to get this and check if it's some. And this all needs to be shared. And this, for some reason, is wrong. Value used here after move. That's fine, I think. Use after move. Isn't this a shared reference? Did I write this wrong? No, it is a shared reference. Oh, it's because of the insertion. Okay, yeah. We should clone this. This should be clonable. And then we do, I think, clone on this. It wants me to clone here. Value moved here. Next position is the direction. Open this up a bit and actually read it. Borrow of move value direction, mute direction. Move occurs because direction has type direction, which doesn't implement copy. Value moved on 71. So when we do the hash set here, that's almost certainly going to be a clone. We don't need it to be the exact same one. We just need it to be the same value. And then that moves us down to borrowed here after move because we're doing an insert on it down here. So the insert can also get cloned. And then we've got a borrow for the IVEC2. That's correct. But that should not be relevant because we construct a new IVEC2 out of that. Moved here in a previous iteration of the loop for get. Because this does need to be that. I guess that's how I set it up. That's true. Okay, so now that we've cleared that up, if visited positions get next position direction clone. So if we are in a position, and I think we need to do this check after that direction, right? If we do this, then we need to do that here. And otherwise, the direction is the same. Same thing here, I think. No, we've already inserted it here. So this would immediately trigger. And this would test the same thing that we have at the beginning. So I think doing this once at the top is fine. Now that I think about the loop a little bit more. And then we're doing a map here. I think we need to do a filter. This loop, no implementation for IVEC and shared IVEC equality. So we either need a shared reference here or a dereference on the new wall. And then this is still an iterator because we haven't collected it yet. This loop, I think, is our determination about whether it's looping or not. So if it breaks here, it's not looping. If it breaks here, it is looping. So this is a vec of all the positions that have caused a loop, I believe. Let's bring this all the way down to the collect. So we can actually do the type signature here, or we can do the type signature turbofish style on the collect. I think because it's hard to see whether this collect error is out or not. If we don't do it here, we're going to do it here. And then results dot length, I think, is what we need here. And hopefully that's 6. Looks like 0. I don't know what's debugging out there. I think that's just that's the run. So we actually do have a problem for sure. And here I'll debug results, I guess. So results is empty. So the logic is wrong here somehow. I guess they all break here, right? So they all break false. Why do they all break false? I don't know, but let's debug. I guess this doesn't need to be in this if. So we could stick this up here for clarity, right? Next position, if the next position has a wall in front of it, or is a wall, I guess, is the more accurate way to say that. If the next position is a wall, then we need to turn right. And actually the position doesn't change in that case. So we just continue. And then if visited positions has a match for the next position and the direction that we're going, then we have to break out. Otherwise, if that position is inside of the grid, set this. And I'm adding these continues for my own clarity here. So the question becomes, why is my condition incorrect? If the next position and the direction already exist in the set, that's what indicates a loop, right? For the test, there were 42 locations or something like that, right? It's a lot. It's a lot to check. Let's do this. Iter take 1, just check the first one. I think tracing would help us here too. These debugs are getting kind of noisy. So here we end up with 7, 8. That doesn't sound right. Our starting position is off. Did we not reset the starting position for the guard, right? Original guard position, loop and whatnot, visited positions. We didn't. We did not. So to make this a little bit easier, we'll reuse the same name. Shadowing is a little bit annoying there. If the guard isn't starting in the right position, that's really bad for us. Yeah, we get significantly further when we start the guard in the right position. So let's take that take out, and the test is passed, I think. Let's make sure that this is actually passing. So this 6, I don't know, let's make it 67. Then we get a failing test. So our logic was correct. We just didn't have the right guard starting position, it seems like. Let's get rid of this debug as well. Can leave that info there. It won't output unless we tell it to. So the logic here is kind of like finicky and complicated, but kind of hoping it just runs. I'm mostly concerned about the runtime of this because let's start it with like debug. I'm concerned about the runtime of this because I kind of wrote this in a very messy way, and we have to do the simulation for all of them. And if we messed up any of the loops, then that's a big issue. So it didn't run fast enough for me in debug, so I'm going to add the release flag here. We've always been running with debug so far, unless we're benchmarking, but we'll see. Yeah, see how much faster that run? I didn't actually check how long. That's also the right answer. Perfect. I didn't check actually how long the debug was going to take. So maybe we do that for fun and just let that run for a second. But the actual release build took 7 seconds total, including the build itself. It actually had to do some build here. So the difference is 7 seconds for the build plus, I guess, 24 for debug and 2 for release. So notably useful to use -- release. This will become important later on in Advent of Code problems, especially if you're doing what we're doing here. And we chose to just like actually simulate the guard walking around everywhere. That won't work for every day moving forward. We will have to come with algorithmic approaches at some point. This is fairly messy, I feel like. But TLDR, we took our logic from part 1. We added this original guard position as well, so we could keep that around. The original loop sends the guard around in all of the positions they need to be, or the positions that they would travel on given the default settings. That gives us this list of visited positions, which we put into a hash set. We removed the original guard position because we can't actually place a barrier there according to the rules. And then we iterate over all of those, which then gives us a new wall to calculate. And then we need to use basically the same logic for the iteration. I think this could all be cleaned up, but I'll have to decide on how to do that. This is all the same logic that we have above, with the big difference being the hash set that we're using for the visited positions stores the guard position as well as the direction they're moving in. The reason for that is we need to do some kind of loop detection at some point. And the easiest way, the most straightforward way for us to do that is to store the positions we've been and the directions we've been going on those positions. And if we ever line up with one of those, that means that we will continue the loop. So then we get to use the loop keyword to do our iteration. We calculate the next position using our direction enum. We get from the walls to see if there is one there. And instead of cloning walls every time and pushing this into that hash map, we just are referencing walls here and then adding another if to see if the next position is actually equal to the new wall that we're checking to. If it is, then we need to turn right. We have some tracing logs here that we were using. If that visited positions ever matches a previous one, then we need to break, and this is a loop. If the guard's next position is within the grid, then we just keep them going. And otherwise, they're outside of the grid, and thus this is not a loop. We chose to collect that into a vec of ivec2s and then do .length. We could also do .count here instead, and then we don't need to do .length because this will just count the number that we've filtered over. And we'll just run our test to make sure we didn't break anything there. I think count is more appropriate here. I do like the idea that we could log out all of those ivec2s, but we could also do that here with .inspect if we wanted to. And then that would allow us to, let's say, run day 2, part 2 release. And this is all of the positions that are coming out of that iterator. There are 1,400 of them, so I'm not going to go look at all of them, but we can still retain that information without needing to collect here. I anticipate that our benchmarks are going to be slow today. I think that the benchmark for part 2 would probably take a pretty ridiculous amount of time to run. I think it took 2 seconds total for the actual runtime. So almost I feel like benchmarking this isn't even worth it. Our parser is slow. Our logic is, 300, 400 microseconds for part 1. Part 2 gets even worse. We're not doing this mathematically. We're doing this kind of in a brute force way. We're just simulating the guard walking around everywhere. There are definitely ways we can skip. I think, for example, one of the things that we could do is go from rock to rock to rock to rock to rock. We don't actually need to iterate over all the positions, so maybe I'll try that in the refactor tomorrow. And depending on how big this grid is and the input, which I didn't actually look at, that could alone save us, I think, a decent amount. Yeah, this is a 100 item grid, so that could save us a maximum of like 128 if we were down here and we went all the way to the top. So I think that's it for today. This benchmark's going to take forever to run. If it finishes, in a reasonable amount of time, I will put it in the description. It'll be in the benchmarks file anyway. So that's it for today. I will see you tomorrow for day 7. We're almost a week into Advent of Code. Wow. Hope y'all are still hanging in there. Plenty of days to go. Have a great rest of your day.